did. So we'll talk a little bit more about that on Thursday. Today, what I'd like to do is what we were supposed to do on Thursday, start water chemistry. And how many people are geochem? Right. So geochemistry is really one of the most interesting things to me about geology. So I really love geochemistry. I love learning about it. And one of these ideas, almost like lithofaces, there's this idea of hydrophases, that different chemistries of waters kind of have this environmental signature. So you can tell something about the water just by its chemistry. All right? And if you look, today we're going to play around with TDS. This was one of the things we were talking about on Thursday. You guys remember what TDS is?
Total dissolved solid.
Total dissolved solids. This was one of the first chemical measurements that geochemists made. Do you know why?
Isn't this?
So before atomic absorption, mass spec,
Because it was all about like early water treatment because of sewage, wasn't it?
did they have mass spectrophotometers hundreds of years ago? Doesn't it sound like it might be really easy to just filter water through a paper and just dry the paper and weigh it and measure total dissolved solids? So this was one of the earliest measurements of water quality indicator. The more dissolved solid, so the more TDS, the older the water. Okay, that's generally the idea. So rainwater would be the least TDS. So the oldest water would be the most saline, the most total dissolved solid. That smells really good. Okay. So today we're going to look, so if you don't have any fancy schmancy chemistry equipment, you can tell something just by TDS. All right? And so that might be something we do. We can dry, we can put water through a Wattman filter, we can dry it, we can weigh it on a scale, right? So that's something that we can definitely do research projects on here at Fresno State. All right. And so we'll talk a little bit about this some more on Thursday. Hickok has this really good kind of evolution over time of water and how the chemistry of the water changes over time. All right, and so TDS, even if we can't measure nitrate, calcium, chloride, you can kind of get an indication of probably if it's older, the more TDS, the more like this your water would be. All right, the fresher the water, it's probably something up here. And we'll go over these a little bit more on Thursday. I think it's one of the things that the geochemistry groups can actually look at and try to see where's the water in our system here. And what the group found last time was that our youngest water that they were using to wash the dairy pond was actually some of the oldest looking water. So we were chemically perturbing water. So it's really interesting. So I'm going to hand out this lab, what we were supposed to do on Thursday. We were invaded by an awesome rat story. And we're going to do the first part today. The second part, so the first part is really just this TDS, this total dissolved solid. The second part will be the Piper diagrams, which I think that we had a really good intro from the group. So we can kind of use these as some really important indicators of water quality. Before that, though, I wanted to show this small video. It's a little bit dated, but it talks about how just very small amounts of things in groundwater can, over time, have really bad health effects. So this isn't just arsenic that's a problem. I just wanted to show you guys that it's really, really small amounts of things that can be a big, big problem. And here in California, New Hampshire has problems, New England has problems, there's arsenic everywhere, right? And who was at the arsenic symposium? Do you remember what other elements of concern were mentioned here?
Uranium.
Uranium,
Lead.
Aaron Brockovich,
Dimethyl.
chromium,
PCB.
chromium, nitrogen. So those are the big ones here. municipality water supplies, what? And so, I want you to understand, we're gonna be looking at maximum contaminant levels. These are things that World Health Organization, EPA, try to set as standards, drinking water standards. Ideally, the risk is, do you remember what they said? The toxicological risk? What's the toxicological risk of anything that somebody produces? One in a, that's the arsenic problem. 1 in a million. There's a 1 in 1 million chance that you get cancer from this. Arsenic at 50 was 1 in 100. At 10, it's still 1 in 500, which is order of magnitudes away from the ideal, right? How do we know what effect? How did we figure out that 1 in 500, 1 in 100 number? You guys know how we find out toxicological effects? You can do mice models.
Count the bodies.
You can count the bodies. Those are the two ways we understand toxicological effects. Mass contaminations, accidents, and using a mouse or some other kind of model to mimic humans, what effect it would have on humans. Right? And so that does a really good job to show that even at very small amounts, and a lot of people here we're always arguing about amounts of water, right? Oh, give me my water, don't take my water away. But they're not talking about what's in the water. Kind of need both. All right. And so there is some chemistry in water. Don't forget that. People will. And that chemistry has effects on people. So I handed out this water chemistry lab, lab 5. We were supposed to start this Thursday. And we're getting to it today. What I'd like to do, so we're all on the same page, I'd like for us to go around, read the paragraphs one at a time together, so we're all on the same page. And then I will think for today, we'll just do 1 through 11 on page 36. And so if we read the intro together, we'll actually look at total dissolved solids and how we can use that as an indicator of water quality, or how it's actually used, so get a feeling for that. You want to start, Matt, in the back?
Okay, sure.
Introduction.
More than 99% of the dissolved solids in natural groundwater is composed of fewer than a dozen constituents. The bulk of these consist of only 7 ions: calcium, sodium, magnesium, potassium, I forget those, dissolved silicate dioxide. Routine chemical analyses of water samples report these constituents so they can be used to provide information both on the aquifer materials and the suitability of water for human use, often referred to as water quality.
Yeah, and so they have this table, 5.1, it's also there. And you can kind of just get a sense looking between those major constituents. These are the things that are typically measured, right? The major things. And you can see how they're kind of different between raw rainwater, groundwater in unconsolidated deposits, so maybe the Beddoes zone, igneous rocks, sedimentary rocks, and carbonates. If you look at the TDS, you can kind of see, where is it highest? TDS is highest in which one? Sedimentary and what's the yeah, carbonates. So TDS is the highest overall in seawater. Would you be surprised that, or why shouldn't you be surprised that the sedimentary rocks and the carbonates have the highest TDS? So they're usually deposited in marine environments.